Okay. Hello again. And if you're wondering what does this say, it says, bah, humbug. Look, Christmas Carol, Ebenezer Scrooge. Go from there. All right, guys, for my AP thugs, now you are going to watch a video that I've made. Okay? Whether you want to admit to it or not, you're going to have to. This is a review, and I figure many of you would like to have a review and maybe get a little bit more clues as to what might be on tomorrow's quiz. Maybe. Okay? Alright, so we've been looking at Chapter 5. Chapter 5, the exam for Chapter 5 is not covering all of Chapter 5. It's only going through Dalton's partial pressures. So that is actually on page 12. Okay? This would be the last slide that you are responsible for, not the water vapor pressure. No. Up to here, and that's the end. If you go beyond this, that's on you. Alright? So we do, it seems like there's an awful lot here. What do we need to, what is it that we need to know? Okay? What is it that you would be, one, I would be familiar with some concepts. I would be familiar with some vocabulary. Concept, for example, pressure. What is the idea behind pressure? Okay? I would expect you guys to understand how a barometer works. Okay? The idea of, hey, sketch a barometer and show me how it works. That probably would be an interesting thing to do. Or maybe I may have you sketch a manometer and have you show me how that works. And how does that, how does the manometer actually work? Now, of course, now here down we're looking at the units of pressure. I have not given you my Vamos a la Playa chart. That is the pressures at the sea level where you guys can go and be able to switch from like atmospheres to kilopascals to pounds per square inch. But if you notice, the stuff pretty much that we've used here are atmospheres, kilopascals, and torr. That's all. Now, millimeters of mercury is also fair game, but you will have that ability. I can turn around and have you convert from one air pressure thing to another. And you should be able to know how to do that. That would be like a cross multiply divide type thing. So if I have here, if I have, for example, 2.5 atmosphere equals, how many kilopascal, okay? When you look at something like this, well, I'm going to go ahead, go 2.5 atmosphere over X number of kilopascal, and that's going to equal, and here's the key thing that you've got to pay attention to, you have to deal with what's at the sea level, okay? Yeah, somebody was knocking on the door. So you have to pay attention to what is at the sea level. Well, what is exactly at the sea level? At the sea level, we have 1 atmosphere over 101.3 kilopascals. Solve for X. That's it. That's all that you would need to do to go and convert. All right? All right, let's move on here. Okay? So you should be comfortable with converting pressure units. Okay, gas laws. Like Boyle's law, oh gosh, P1 V1 is equal to P2 V2, okay? Would you have that formula on the exam, on the quiz? Yes, you would. I'm not having you guys memorize the formulas. I'm not having you guys memorize the constants, okay? Unless you are particularly annoying to me, all right? That should not be an issue. So you should not have to memorize constants, you should not have to memorize Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's law, combined gas law. You should not have to do that. That's all pretty straightforward. Now, if you think about the combined gas law, P1 V1 over T1 is equal to P2 V2 over T2. Okay? It wouldn't matter because that takes into account Boyle's law, Charles' law, okay, and Gay-Lussac's law, all in one fell swoop, which is really, really sweet. Because with Boyle's law, if the temperature is constant, then you're only dealing with pressure and pressure and volume. Okay, if you're dealing with Charles' law, pressure's constant, you block that out, and you got yourself volume and temperature. And that's it. So I might throw in a problem or two on that one, okay? But you should be comfortable with that, okay? You should be able to do problems with these laws. You should be able to be comfortable in calculating this stuff. All right, now keep in mind about these laws in compared to the ideal gas law. Now, the ideal gas law is PV equals nRT. This here, this is taking a photo of the gas now, or I like to call it, this is the selfie. This is the gas selfie formula. That's exactly what this is. This, you have a before and you have an after. Okay, now how can you tell which one is which? My problems are going to be fairly straightforward. I'm not trying to trick you guys. I'm trying to see what you guys know in terms of solving problems. That's basically it. Okay? Any questions? Of course there are no questions because I'm talking to a camera. All right, let's move on. I know you guys aren't laughing. You're not the type to laugh very easily. Okay, Avogadro's law. Yeah, Avogadro's law basically deals with moles. That's basically it. Okay? Combined gas law, you guys already know that. Now, ideal gas law, we kind of went over this, PV equals nRT. And with that, of course, there is the, what is the R? So if we got PV equals nRT, R is what, it's our gas constant. Now, the key thing about that, ladies and gentlemen, is that it's going to be 0.083. That's our constant. I am not going to worry about the units because that's just spending a bunch of extra time on that, all right? But again, this is a very important number that you guys are going to be using, all right? Now, when you are converting, remember the temperature has to be in Kelvin, okay? And I'll give you the formula for that. All right, in this case, I'm just going to stick with 273, although on the exam, you should do 273.15 to be technical about this, okay? So the temperature should be in Kelvin, absolutely, okay? Let's see. Equation of state, yeah, you should be familiar with the idea of the equation of state. All right, it's you go from point A to the start to the finish. It doesn't matter how you take the path to get from the start to the finish. Okay, you can't, there's no other way around that. Equation of state probably would be good to know. Okay, examples. Okay, you should be comfortable in doing examples of laws with PV equals nRT. All right, I would like to point out the gas density and molar mass. That would be page 8. That last slide down here, I'm showing you specifics, okay, where the molar mass is equal to density times R times T divided by P. Probably that would be a good formula to be comfortable with. Where N stands for molar mass, think in terms of grams per mole, okay? Okay, as we go on here, you should know, I'm on page 9, you should know the standard temperature pressure conditions, okay? Standard temperature pressure conditions, what are they exactly? Well, the STP is 0 degrees Celsius, 1 atmosphere, okay? That's your standard temperature, that's your standard pressure. You should also know that 1 mole gas equals 22.4 liters. This is only true at standard temperature pressure conditions, STP conditions, okay? Now, again, examples there, you should be able to do it and be quite comfortable doing this. All right, now you have a whole bunch of other examples that I believe I have made some videos off of that for you guys, so you should be paying attention to those. All right, and then the next thing that we got to deal with is Dalton's law. Okay, as I'm winding down with this. So Dalton's law, what's the idea behind this? Well, Dalton's law is basically saying if you have a number of different types of gases in a container, okay, so if you have a container and let's say you have different types of gases in there, then each gas is going to exert their own pressure. And that's what we talk about, the partial pressure. Partial pressure, think of it as part of the overall pressure. So if I look at the total pressure, that's equal to the pressure due to the hydrogen plus the pressure due to the chlorine plus the pressure due to the helium. This is what Dalton's law was talking about when he mentioned about partial pressure. Think of partial as part of. Now, combined together, they get a total pressure. That's the idea. All right. So when we look at Dalton's law, we also get to look at the mole fraction. Now, for Dalton's law also, as we are down here, okay, we are down here with Dalton's law, and the P total is equal to the total number of moles of gas times RT divided by V. Okay, but there's also the ratio of the moles, something called the mole fraction, which we use the Greek letter symbol chi. Why do they choose that? I don't know. But the idea about this is it's a mole fraction. This is a number that does not have a unit attached to it. It's unitless. So when we look at something like for the mole fraction, okay, we're at the bottom of page 11 down here, okay, keep in mind that we can look at the number of moles of the individual gas divided by the total number of moles of gas of all the gases combined. This is one part of this mole fraction. Now, we can also look at the partial pressure. We can look at the pressure of gas number one. We don't have to know the number of moles of it, but we can compare that to the total pressure. So we can think about, you can think about it, you know, we call it a mole fraction, but you can think about it like an ordinary fraction. It's a ratio. If I have something, if I have got a container that's got 3 gases in it, okay, if I have a container that has 3 gases in it, okay, if the total is 4 atmosphere, okay, and let's say H2 has a pressure, the pressure of H2 is 2 atmosphere. What's going to be our mole fraction? Well, our mole fraction is going to be the partial pressure of the hydrogen gas, which is 2 atmosphere, divided by the total pressure, which is 4 atmosphere. So our mole fraction would be 0.5. That's it. That's all that it is. It's not too bad, but that's the general idea with that. Okay, and I'm flipping over to the next page as I'm wrapping up here for this. All right. Now, what about the idea about those containers, where we had this container, we had this container, and then we had this container? When we had those containers, let's say it was 3 liters, 2 liters, and 1 liter, okay? Then we could look at the type of gas that it is. Okay, let's say this is H2, this is Cl2, and this is He, for the sake of argument. And we can look at the pressures that each one is individually putting out here. So we can go ahead and we can say, all right, 1.5 atmosphere. Here it's going to be 2.5 atmosphere. And then over here it's going to be 5 atmosphere. Holy cow, the helium is under a lot of pressure. Okay, so when we look, and then of course now these are stopped up, so they are in their own containers. And the idea about this is, well, hey, what's the partial pressure of the hydrogen gas? Well, if we look at the partial pressure of the hydrogen gas, and let's assume we open these up, so now the gases are able to freely mix throughout the whole thing. Now that the gases are able to freely mix throughout the whole thing, what is that going to look like? What's the partial pressure of the hydrogen gas? Okay, what's going to be the partial pressure of the hydrogen gas? Well, the partial pressure of the hydrogen gas is going to be 1.5 atmosphere. Okay, that's the partial pressure. That doesn't change. The partial pressure of the Cl2 is 2.5. The partial pressure of the helium is going to be 5 atmosphere as well. Now if we look at what's the mole fraction, if we look at the chi of the hydrogen gas, that's a little bit different, because now what we got to look at, ladies and gentlemen, is we have to look at what's the partial pressure of the hydrogen gas, which is 1.5 atmosphere, divided by the whole thing, which in this case 1.5 plus 2.5 is 4. Plus 5 gives us 9 atmosphere. So if we look at this, we can divide that out, and we're going to have a decimal place out of that. Okay? So that's the basic idea here behind the review. I'm hoping that this will help you guys out a little bit. All right? If you're still kind of stuck, you can check the other videos that I've got uploaded on YouTube, because I only really started uploading those things basically for Chapter 5. At this point. All right, I hope this works, and have a good rest of the day. Take it easy.